So this was the topic that we discussed in the previous class, which is nothing but common mode rejection ratio. Can someone tell me what is this CMRR and how is it so important? Yeah. Basically, if you see this circuit, we should be able to analyze as to how important the common mode rejection ratio is, right? Can I have some answers? So what are we doing here? Basically, we are trying to connect both of the bases together so that they are maintained at the same voltage. So the idea of doing this is that I will have no differences, and that's the whole idea, common mode. Okay, bringing both of the base voltages together. Okay. Okay. And then we saw an equivalent circuit drawn. But then even though we have this common mode setup done, okay, but still, we can find that there can be some amount of noise, okay, slight noises, which can actually, be present in the wires, and because of which, there can be an output, okay, fine. And we also saw the formula for common mode gain, which is gain is actually output by input, and then in the common mode format. Okay, so what is this common mode format? Having the bases connected to the same voltages. Okay. Then we saw the formula for CMRR, which is nothing but 20 log AOL divided by ACM. Okay. So this is your open loop gain divided by common mode gain. Okay. So I have put up this here, okay, so that you can understand that there is a factor called the CMRR, okay, common mode rejection ratio, where the typical value is about 90, and it can go to a minimum of about 70. Right? Then we saw the output voltage in common mode format. So that is input should be in common mode because output follows input. So this kind of configuration is called what? We have studied this. This kind of configuration is called
emitter follow.
Voltage follow.
Yeah, voltage.
Right? Output voltage follow. Thank you. So if the inputs are 3 volts, then the output will also try to be maintained at the same levels. Okay. When the signal frequency increases, CMRR decreases. So CMRR and frequency are inversely proportional. Okay, when one increases, when the frequency increases, CMRR decreases. So they are inversely proportional. Okay, fine. So today we'll be looking into something called power supply rejection ratio. Okay, just like how we had common mode rejection ratio, here also we have power supply rejection ratio. So the reason why we are doing this is because whatever changes happens in the input, the same thing gets replicated in the output. So I want to make sure that my inputs to the op-amp are secure. Okay, it does not have any instability. So in order to do this, I have a factor which can calculate. Okay, and we will just look into it. As in the case of common mode signals, supply voltage variations do produce some output voltage changes, right? So I hope you all agree with that, isn't it? So which means, which means what is going to happen is, we see that whatever variations, okay, whatever supply variations that we do, what kind of supply variations that we are producing, because the bases are connected, right? So if my voltage levels are increased, we have discussed what is going to happen to the currents IC1 and IC2. Is it going to increase or is it going to decrease? And what is going to happen to the resistors? Yes. So as the voltages change, okay, as the voltage increases, I've told you the currents also will increase. If the currents have increased, then the drops across the resistors will increase. Okay. Do you all remember that, or should we go back to that slide?
We do, sir. We do remember.
Fine. So despite the use of internal circuitry designed to combat them. So even though we have some circuit, okay, to make sure that these levels of inputs are maintained, but still, we can see that it is not. So this PSRR is a measure of how effective the op-amp is in dealing with variations in supply voltage. This is important. Okay, so I want you to actually make and note of this, okay? Which means your PSRR is a measure of how effective. So this can be a very short definition of what is PSRR and where are we using this. Okay, so PSRR is a measure of how effective the op-amp is in dealing with variations in supply voltages. Now I have a question. If in case the supply voltages are made constant, is it a benefit or not?
Sir, it depends on the usage now, sir.
Okay. Usage, can you please be more precise? Like how? Yeah, go on, go on.
Sir, like depending on the user, like for changing the gain, so he'll accordingly adjust the input voltage and everything.
Okay, fine.
The
That
base
is
current.
yeah. That is one way of seeing, one angle of seeing it. But what I am trying to tell here is, if in case we have a stable input, is it advantageous? Is it doing more help to the circuit by keeping the input constant?
Yes, sir. It will be advantage.
Yes, right? So which means this PSRR, okay, is a tool, okay, or is a measure of making sure that this goal is achieved. What goal? Of making sure that we have proper supply voltages without any changes. If a supply voltage change, let's take an example. Okay, let's say about there's about 1 volt of difference. Okay, let me take that 1 volt of difference. 1 volt of difference in what? Supply. Okay, this causes an input offset of 1 microvolt. Then the power supply rejection ratio is 1 microvolt per volt, or 10 raised to minus 6. So just if in case there is about 1 volt difference, okay, in the supply, in the input voltage, then what happens? How do I calculate PSRR? PSRR is calculated as 1 microvolt per volt. 1 microvolt per volt. So for every volt, there is 1 microvolt of change. So if in case 10 volts, then it's going to be about 10 microvolts, right? So one thing that you all should understand is that keeping the input constant is very important. So PSRR is usually expressed in dB, okay, decibels on the op-amp data sheet. So if you see the data sheet, you will find, okay, 90 dB, 70 dB, just like how we saw the values for CMRR. Similarly, you can find the value for PSRR as well, okay. And this is going to be the formula for PSRR, right? So what is it? PSRR is equal to 20 log Vs divided by delta Vi OS dB. Okay. So now this is nothing but some change in your supply voltage. Vs is supply voltage. Delta is, you know, the change, minute change in supply voltage, and the changes in input voltage. OS is nothing but your offset. Okay. Offset. Input offset voltage. So please make note of all these abbreviations. It's going to help you during your exams and internals. Vs is referring to supply voltage. Vi is input voltage. And OS is offset. So when it is IOS, then it becomes input offset voltage. When it is OS, then it becomes output offset voltage. Right? Okay. In CMRR's case, a PSRR of about 100 dB. Now let's take an example. I will say that I have a system, okay, and its PSRR is about 100 dB. So how do I understand this 100 dB? It is nothing but equal to, it has a ratio of 1 divided by 100,000, okay, micro, so 6, okay, keep that in mind. So 1, 2, 3, 4, 5, yeah, so 6 decimals, okay. So if I say 100, okay, then you should keep this ratio in mind. Okay, which means 100,000. Okay, so if I say 200 dB, then it becomes 200,000. Okay, 1 divided by, so the inverse of 200,000. So just keep in mind that you have to add another 3 zeros to it. Okay, so just keep that in mind, and that's going to be in the inverse fashion, 1 divided by. Okay, 1 divided by, that's important. Right. So giving a supply voltage change, okay, so that is nothing but your delta Vs, okay, as I mentioned, delta Vs, supply voltage change is delta Vs. Reduction by a factor of 100,000 at the amplifier input. So which means if I'm saying that my PSRR, the system has PSRR of about 100 dB, then what happens? It can reduce the changes by how many times? 100,000 times. Okay. So isn't it playing a huge factor here? Yes or no? Isn't it playing a huge factor, power supply rejection ratio?
Yes, sir.
So what are we trying to see here? We are trying to see that it is giving us a proper stable input. Okay. So if a system has PSRR of 100 dB, it means that it is reducing the impact, it is reducing the damages by about 100,000 times, where at the input side of the amplifier. Now this is important, at the input side of the amplifier, at the amplifier input. Okay. So So hence, we conclude or we say that this power supply rejection ratio is very important. So using this ratio, we make sure that our inputs are made stable, okay, and whatever these spikes or ups and downs can actually be reduced with the help of PSRR. So a higher number of PSRR is always good because it can reduce the factor, right? It can make the system more stable. Just take the example of your stabilizers. Okay. The stabilizers that you connect for all your electronic equipments. There can be a lot of fluctuations in the voltages, right? There can be spikes in the current, and your stabilizer will have internal circuitry which can help in stabilizing these voltages and currents, right? So ultimately your electronic device is saved, okay, increasing the lifespan, usability of your device, right? So power supply rejection ratio is one such important thing, okay, which can actually help us determine the system's reliability, okay, right. So moving on, power supply rejection ratio is how do we do it? Okay, it is amplified by the circuit closed loop gain, okay, closed loop CL gain, which once again is the non-inverting gain or noise gain. So if we have to say, or how do we bring it out in terms of equation, okay, in terms of a formula, okay, then small changes in output is equal to delta Vs divided by PSRR into ACL, okay. So you should remember this formula, okay. So what is this formula suggesting? What is it suggesting? It is telling us that output voltages, okay, the change in output voltages is dependent on the supply voltage change, okay, the changes in supply voltage. Say for example, instead of 5 volts, okay, I'm giving about 4.7 and then 4.8 and then 5. So all these changes, okay, is nothing but called delta Vs divided by PSRR. So for a system, we can decide PSRR as to how much it's going to be, just like how we saw in the previous section. If it's 100 dB, then 1 divided by 100,000 is the way that it can withstand the changes in input voltages. And along with this, because our output, is a combination of input and gain, right? So we have to take gain into consideration. So ACL, closed loop gain, is also considered. Any doubts here, students, up till this point?
No, sir, no doubts.
Okay. So in CMRR, we saw that, if it increases, then what's going to happen with the frequency? Inversely proportional, right? So the same thing happens here also. PSRR also, decreases with increase in signal frequency. So which means CMRR and PSRR both are same. Okay. So when I say same, it means that if one increases, okay, the other one decreases. Okay. So if CMRR increases, then if the signal frequency and CMRR are inversely proportional. Here PSRR and signal frequency, these two also are inversely proportional. Okay. So This is about your PSRR. So what are you going to write if a question is asked about PSRR? You're going to write as to what is PSRR, okay, the definition. So I've put up here in the first and the second point. And in the third point, I have given an example, okay. Let's say if 1 volt, then what is going to happen, okay. Then you can give the formula for PSRR, okay. And you can say the impact, okay, of 100 dB of PSRR. And then you can conclude your answer with the changes in output voltage, right? So I have tried to make it as simple as possible. So any doubts till this point, students? PSRR, CMRR, any doubts up till this point? Okay. So moving on to offset voltages and currents. So this is going to be a mixed topic, okay, offset voltages and currents. Now we have seen offset voltages here, okay, OS. So this is input offset voltage. Okay. When it is V0 OS, then it becomes output offset voltage. Right? So we are going to look into this in detail. Okay, so just have a look at the circuit and tell me, okay, where we look or we saw this.
CMRR.
CMRR, okay. Don't you think this is the basic circuit of an op-amp?
Yes, sir.
Correct? Yeah.
Yes, basic, sir.
Yeah. Okay. So now we'll be looking into the input and output offset voltages. Now, what is this offset? Offset is nothing but instead of 5, if I'm giving about 5.1, okay, so this 5 minus 5.1, which is about 0.1, becomes my offset. So if this change is at the input side, then I call it input offset. If this change of voltage occurs at the output side, then I call it output offset voltage. Simple, right? Change in the level of voltages, either an input or output, is called offset. Fine. So we will just look into it. Referring to the basic op-amp circuit connected to a function as voltage follower. Okay, so we know that our op-amp works as a voltage follower, meaning that whatever is at the input side, right, the same thing appears at the output side. It tries to maintain the same thing at the output side. So hence the term voltage follower. As seen for a voltage follower, the voltage levels at the output terminal and inverting input terminal follow the voltage at non-inverting input. So that is what we discussed, right? So whatever is here, okay, whatever is at the input, the same thing tries to stay at the output. So the levels are tried to maintain. For the output voltage to be exactly equal, okay, so in order to have this, okay, what we should do, we should make sure that we have both Q1, okay, which is transistor Q1 and transistor Q2. We should have both of the bases, okay, the voltages between the base and the emitter. Okay. Between the base and the emitter. So I will be calling this as VBE1. Okay. And this will be called as VBE2. Right. So this is the voltage between the base and the emitter of the first transistor, and the voltage between the base and emitter of second transistor. So if and only if these two voltages are perfectly matched, okay, then we can say that it's an ideal circuit. Okay. And what is the impact? The output voltage will be exactly equal, right? Just a moment. Yeah. So the output voltage will be exactly equal to the input. So these are the characteristics of an op-amp. So we can see here that we have two voltages, VB1 and VB2. So in order to have a perfect output, so when I say perfect output, without any kind of offsets, without any kind of increases or decreases in the levels of voltages, then I should make sure that these bases do have equal voltages, which means VB1 should be equal to VB2. Okay, so for the first and the second transistor. Is that clear, students? Any doubts here?
No, sir.
Any doubts here? Can I proceed?
Yes, sir.
Okay, fine. So this becomes our initial condition. Okay, so the condition is that our base voltages should be equal. Fine. So we have a formula here, okay, and an example also given, and we will just look into this. Of course, this is going to be our last slide for discussion. When this is not the case, which is not the case, when your bases, okay, when the base voltages are not same, when Q1 and Q2 are not matched, when Q1 and Q2, remember I was telling you, if an IC, okay, is manufactured say by company 1, okay, and it has a batch of ICs to be manufactured. Right? So let's say there are about 10 ICs manufactured in that batch. So IC number 1 and IC number 2, even though they are the same, let's say AND gate, okay, they're not going to perform the same, which means they wouldn't have the same electrical properties and the physical properties. So which means there is going to be slight changes in the output levels, okay, compared to the previous one, right? So similarly, if I have to match these two transistors, which is Q1 and Q2, I have to make sure that the voltage levels are also same. The base voltages of the first and the second transistors are to be same. If in case it is not same, then we see that these input and output offset voltages comes into picture. So when this is not the case, the voltage difference acts as an input voltage, which is referred to as VIOS, which is offset voltage at the input side. So input offset voltage. So I have taken here an example, okay, and we will just look into this and try and understand as to how this happens. Okay. Now concentrate on this section here. Okay. Fine. VIOS is equal to VB2 minus VB1. Now what is this VBE? Quickly, can you please tell me what is VBE?
Base emitter voltage.
Base emitter voltage. And how is this important? How is it important? That's the one which drives your transistor, right? That's the one, that's the terminal where we give input to your transistor, right? Okay. So this is going to be the difference between the two. Okay, suppose VB1 is about 0.7 by default and VB2 is about 0.69. There's not much of difference, isn't it? So my input offset voltage is going to be about 10 millivolts. This is volts, so in millivolts it's going to be 10 millivolts, right? So you can see that there is a substantial change, okay, when both are not same. So generally we want them to be about 0.7 volts, okay, taking ground into consideration. Okay, so we refer to it as 0.7 volts above ground. Okay, 0.7 volts above ground. But here what is happening, instead of being 0.7, it is going to be about 0.69 above ground. Okay, above this point, which is about 0.7. Okay. So consequently, what is going to happen, because there is change in the input, as I told you previously, whenever there is a change in input, the voltage, due to the change in input voltages, the currents are going to change. And because of the change in currents, the drop across resistors are also going to change. Okay. So this output voltage, okay, which is getting affected, and minus 10 millivolts is actually coming instead of 0 volts. Do you all agree with this? Yes. Minus 10 volts instead of 0 volt, right? So if in case it is giving me a 0 volt, then what kind of transistor is it? Yeah. If my output voltage is giving about 0 volts, means what do we understand by it? Right. So here, we are looking into the offset voltages. So just because of this minute change in the input, okay, what is going to happen? We are seeing that this minus 10 millivolt is also going to appear at the output. So instead of being a 0 volt, okay, instead of it being 0 volt, okay, it's actually giving me about minus 10 millivolts. So if in case it was giving me 0 volt, okay, then I would call it a perfectly matched transistor, right? Because the differences are cancelled out and I'm going to get a 0. But here the differences are not, there is a different voltage, right? You can see that there is 0.7 here. You can see that there is about 0.69 here. And once we minus them, we are getting about 10 millivolts. So this is what is going to appear at the output side. So hence I am not getting 0, but I am getting about minus 10 millivolts. So in this case, do you say that these transistors Q1 and Q2 are perfectly matched? Are they perfectly matched in this case, giving us minus 10 millivolts?
No, sir.
No, right? So if I want a perfect 0, okay, then it means I need to match them properly. Okay. So just to recall, okay, this Q1 and Q2 should have the difference to be 0. Of course, these two are acting as a differential amplifier. That's its job. Whatever the differences, those things are amplified, right? So if I maintain same voltages V1 and V2 or Vi and V2, right? So then the difference is going to be 0. The differences are going to be nullified, right? So that is going to be a perfect op-amp, right? But in practicality, we cannot attain, okay, such things, and we might sometimes force the input voltages to be different. That's when these concepts of power supply rejection ratio, CMRR, all this comes into picture because of the non-ideal properties of an op-amp, right? So I think we will stop here, okay? And in the upcoming class, I will be giving you the formula as to how this offset output voltage, okay, is calculated. And we will probably look into few numericals, okay? And we will see how CMRR, PSRR are all calculated.